Thank you, everyone. Let me start my timer, actually, so that I don't go over. Hello, everyone. Thank you for being here. I'm going to talk today about building reasoning agents with reinforcement learning. So for a bit of context, at AdaptiveML, we build essentially RL ops tooling for enterprises. So essentially tooling that enables companies to run reinforcement learning on their model, to specialize them, to do a bunch of things with them. And one of the things that often companies build with our tooling is what we like to call reasoning agents. And this refers to an idea which is that, very typically, kind of what I want to almost call the previous wave of agents was very explicitly defined. Maybe you are used to, you come into LangGraph or something like this, you explicitly define, the transition, the behaviors of the agent and all of this. And actually, in that paradigm, the model has very little intelligence. It's very limited. It's on tracks. It's on very limited tracks in terms of what it needs to do. And I think a lot of you are probably also very frustrated by this. In a bit more sensitive version of this slide, I have an example of a graph of a company we work with of the agentic graph, and it's I can't show it unfortunately because it contains confidential stuff, but it's a spaghetti mess. And I think probably you have that experience as well of eventually, okay, it's very simple, and then it becomes a spaghetti mess of insane long graph, thing from one another. And what I want to present today is that actually there is a different way to do this through reinforcement learning, where actually in reasoning, the models can handle, all of that all of this essentially transitions and handling the organizing, planning, and executing the function calling and the tool used by themselves. And this is something that you are all somewhat familiar with, actually, because you probably all have used GPT-5, and GPT-5 does some of that, as we will discuss. And we'll discuss a bit more about, how does the reinforcement learning enable that. So I'm gonna first start with a few general trends of where does this come from and where this idea is coming from, kind of how it has been built to position it a bit. A few observations on how people actually implement this in production and how people approach this, so kind of high-level pointers on what we see. And at the end, I have also two actual real-world examples that we have done with companies where we have deployed this sort of system with some interesting benchmarks and lessons learned. And we leave plenty of time for questions at the time. I think it's worth first to take a step back on what are AI agents. So this is a very hype name. It's a name also that maybe for some of you is connoted in a bit too much hype. I don't know if you remember, but 2 or 3 years ago, there was a first wave of agent that is best left forgotten in history, with stuff like baby AGI. I don't know if you remember this repo on GitHub. Yes, this was slap. So this wasn't the best, and it didn't work really well. And I think, because of that, some people are a little bit, iffy about agents and the terminology around it. A way that I personally like to define an agent is actually from a concept that exists in the description of nature, of ecosystems, and of animal behavior, which is the concept of agency. And the idea of agency is the capacity of an actor to act in a given environment. The capacity of a model, to take action. And this is a really important part eventually, it's to take action. It's because we are going towards models that are not just, kind of just doing Q&A or ChatGPT, can you help me, diagnose my cold, but to models that will actually take action into the real world, maybe do things on your behalf, do things on the behalf, help a customer, rebook their flight, that sort of stuff. And this is something we strongly see in enterprise right now, where there is a massive shift in terms of going from models that are purely copilots, they are purely assistants, to models that actually perform tasks that humans would otherwise. And from just to step aside for a second, from an ROI point of view, it's very obvious, because a lot of these copilots deployments have not really brought any ROI to the enterprise. When you read all of these studies or AI deployments, adoption enterprise is failing and all of that, a very large reason is because if the models do not have, the autonomy that we have as an employee of the company, obviously they are not going to bring the same economic impact. And so obviously it's just going to be, you're going to pay for an AI license on top of paying for your labor force, which is, is just additive, and you're just going to be paying more at the end of the day. And so really the wave that we're starting to see in enterprise is actually enabling models to take action and to actually, replace people and actually, drive, cost savings or, performance optimization in the enterprise. I'll skip quickly over this. There's a bit if you think about big trends, about big trends in terms of progress of models. I think, obviously there was the emergence of very large-scale pre-training in the 2020 with GPT-3. Then a very big one was the emergence of post-training, reinforcement learning, and specifically on human preferences initially, with ChatGPT. I think this was a big moment where a lot of people actually not only discovered RL, but discovered AI at large. At least I can tell you in my family, for my parents and grandparents, this is when they understood what I was working on, which was a really cool moment. But yeah, so really this idea of using reinforcement learning to go beyond, just web data. Actually, to the point of the speaker from Poolside before, web data is great, but at the end of the day, it's not super representative of everything that we want to do with these models. And instead, with reinforcement learning, we can learn from a much wider spectrum of signals. And that can be human preference, but that can also be verifiable tasks, so code execution or that sort of stuff, or even, mathematics, like, for instance, formally verifiable problem. I think the breakthrough moment for this was O1, and a bit more in the public, DeepSeek R1 earlier this year. And once again, this is still using reinforcement learning, but on a much larger scale, essentially. That's the main difference. But to my point about tool use and agents, actually, I think the moment where we started really stepping into agentic behavior more truly is actually this year, and is something people didn't necessarily notice too much, but with O3 and GPT-5. I assume everyone in the room has used GPT-5, and you may have noticed that GPT-5 is really good at actually being more factual. So my main usage of GPT-5 personally is not actually a work usage, it's a personal enjoyment usage where I'm trying to learn some physics, and I use GPT-5 a lot to ask it questions about stuff, like trying to understand exercise scenarios and all of this. And before, there was a massive issue where GPT would systematically hallucinate at some point, like a calculation, will try to do it and will do it improperly, and then it will be all slop from there on. It's interesting that GPT-5 doesn't do this nearly as much. And if you look into the chain of thought, you can get to know why. And the reason why is that you will see that GPT-5 almost always generates code to verify its assumption. Actually, you will see it almost never do mathematics by itself anymore. It will always execute code. Even if you ask it to do like a multiplication, you will see it run the multiplication in Python, which is quite funny. And by the way, it does both try it by itself first and then check the result with Python, which is kind of an interesting thinking dynamic. Also, web search is really big. You will see it do this a lot. Bring factual information through web search. Bonus point to whoever can say what physics problem this is in the question section. The question that remains here is, so obviously this is very powerful, but when you are thinking in enterprise, and by the way, I'm sorry, I talk about enterprise, maybe it's not super exciting to you. Most of our customers are boring, they are large companies, but this is the reality of where there is economic impact in this. And so actually there is a very boring question of like, okay, web search and Python code, that's really cool, but how do I bring in, information from all of the databases that you have in enterprise? So this could be like, thousands and thousands of SQL or whatever weird format it is. How do we interface with all of the APIs that you have? So for instance, we work with one of the largest airlines in the world. At some point, the model needs to be able to tell you where is your luggage when your flight runs into issue. To do this, you need to access the lost luggage tracking system, which was built in the 70s and still uses the same code, still run on the same system. And you have to generate this essentially arbitrary code, which looks closer to Fortran than to anything else, to be able to query that system. Well, how do I make the model able to do this? Because if I want the model to be able to undertake that task, I need to be able to do this. And this is really, I think, the big question right now with these agents is actually enabling them to have this panoply of tools that they are going to be able to use to do this. And I think the difficulty here, and there is, by the way, there are other, I think, really interesting things like computer use is also a really big part of this because obviously some stuff is not via an API. Your Salesforce, for instance, environment, you might want the system to interact directly with it. The question of having many agents interact together, like being able to spin off sub-agents, that sort of stuff. But the big one that is of interest to me and that I'm going to talk a bit more about is customization, is how do you enable models to learn new tools? Because yes, and it's true now in GPT-5 as well, you can pull up an MCP, connect an MCP, and hope for the best. I don't know how many of you have tried this. It's not great. And especially when you need to compound the tools. So the model might be okay at like calling a tool quickly and be like, okay, there is this simple tool that can tell me the weather at like a geographical location. Yeah, the model can zero-shot this, obviously. But the loss luggage tracking system I was talking about before, even if you put it behind your MCP, it's not happening. And even worse, very often, you have to compound these tools. So first I look for information about X and about Y, and then you compound it together. Back to the airline, the model can do compensation, so can issue you compensation. But the amount of information it needs to be able to issue a compensation is really large. So it needs first to identify in which regulatory framework you are. Because depending on your flight, on your nationality, there are different rules. So it has to interface with a rule-based engine for this. Then it has obviously to find all of your information to feed into this. Then it has to ask you for your receipts of what you want to be reimbursed. For instance, the meals that you get at the airport. It needs to run OCR. It needs to run the receipt. It needs to run fraud detection on the receipt. Then it needs to actually, get the compensation going to your account. Like all of this, it needs to do this all at once. It needs to plan for all of this. So this is quite complex. And models right now can't do this out of the box. In fact, it's questionable they will ever be able to. The problem is somewhat ill-posed, if you think about it. If you look at an MCP spec, it's quite light. And without the ability to experiment, with like, oh, this is how this API works, this is how I should compound them together, for the models to learn it on the fly, it's going to be quite difficult. So one thing that's really exciting in this is reinforcement learning. Because with reinforcement learning, we are able to teach models to use these tools on the fly. And this leads to, so I will skip over this one. This is a slide that I use more for other kind of talks, more doomer kind of talks, which I will skip for today. We can chat about it afterwards. It's very funny, the progress of AI actually is like almost doubled in terms of acceleration speed by the use of tool and of reasoning. It's quite a funny observation. So the previous paradigm was back, to really what is the core subject of this call. The previous paradigm was to define, explicitly all of this state transition, all of these things with of how the model should interact. And this was like, a complete fuck up of long graph stuff, which none of us, really enjoyed. What's really exciting now is that actually the model can define all of this at test time. The model essentially has access to a tool library, and in its reasoning, will create this graph at test time. So at test time, the model in its reasoning, will plan for what to do, will build all of this. And how does it do this at test time? Well, because during reinforcement learning, this is implicitly trained. Because if you do reinforcement learning on this model with like access to this tool library, and you have an environment where you have a set of scenarios of inputs and a set of target outputs of what you want to achieve in the environment, that's it. That's all you have to do. And by the way, this is very unexciting technically, I realize, because the difficult part is the engineering of RL. But like from an algorithmic perspective, all you have to do is to have these environments, these test environments, in which the model is going to be able to run through scenarios. When you hit the end of the scenario, you reward the model, and through the entire reasoning, you have the entire trace. So you have a single rollout which contains all of the calls to the tool, all of the interaction, all of that which you are optimizing with reinforcement learning. So now this entire graph, which was before something that like data scientists had to toll away at and like constantly fail to cover for all scenarios, this entire graph is internalized essentially into the model and is trained end-to-end with reinforcement learning. And this is extremely powerful. This is a paradigm that works extremely well. And by the way, this is a paradigm that I think applies to pretty much any usage of models, even stuff like RAG. I'll give you, I'm sorry, and I don't have a slide to illustrate this, so you will have to listen to me to picture it. Building a RAG system really sucks. I think it's an experience we have all had, where we hope that there is some magic solution to having RAG just work. And it turns out that we end up like, how do I do the query rewriting? Oh, well, now, wait, what vectorize the stuff? Do I retrain the embedding and gain 0.1% accuracy? How do I do the re-ranker separately? All of these are like Lego bricks that are extremely brittle that you have to assemble. But there's a different way to do this. Firstly, you are never going to get any good results from just tuning embeddings. You are trying to distill into very small vectors a tremendous amount of intelligence. This is never going to work. You are essentially trying to scrap, the scraps actually on the ground. The model needs to be at the center of this. So use vector embeddings, obviously, but like keep them simple. But put the LLM at the centerpiece. Because imagine now that in this tool library, the model can make its own RAG query. The model can access, the basic RAG, just by itself. You don't need any query writing, you don't need any re-ranking, because all of this will be learned by the model during reinforcement learning. And this is genuinely a behavior that we see, by the way, where when you expose a model in a sandbox with access to tools like RAG, the model will learn to overfetch, so like to fetch maybe like 20, 40 documents, filter them like unto itself, like say, okay, these ones are relevant, these ones are not. It will learn to rephrase the queries, to be like, oh, actually, this wasn't that good. Like, actually, this wasn't exactly what I wanted, let me change, to like follow up on information and all of this. And this is insanely powerful. And now you have moved from building a brittle RAG system to building essentially deep search. This is exactly actually the paradigm of how this deep search system works, is because you are optimizing end-to-end. And that's really the big change, is that instead of like having all of these little bricks that are very brittle, now you have an end-to-end optimization of the entire system with reinforcement learning. And reinforcement learning, is incredibly good at optimizing a large language model. Like, it will find anything. Like, it will find all of these patterns, that we have taken years to invent, like query writing and all of this. It will find them, essentially in a few steps. You could also force the model to find them with like some warm start or that sort of stuff, but that's a bit beyond the subject of the talk. Why is this paradigm really cool? I'll skip over this. Another aspect of it, and I'm sorry, this is more enterprise slop, I'm really sorry. But I think it's actually quite interesting from a development perspective, is that we shift how you think about developing models. Because now, with reinforcement learning, there is a sentence that I like to use, which is, if you can measure it, you can optimize it. And actually, this is true. I think this is the best description that's possible of reinforcement learning, is from the moment that you can measure an outcome, you can optimize for it. And that's the magic of it. So that means that now, most of your development process actually is spent in the first phase, the measuring. So you are gonna work a lot essentially on defining, what are like the outcomes that you want out of the model, building rubrics for this, like of how, describing essentially what does a good outcome look like. Based on this, instrumenting measurement of this, probably you are gonna use a lot of AI judges. This is, I think, the magic of LLMs. Which is that, once you have defined rubrics, once you have defined criteria, in natural language, you can use AI Judge to verify this criteria as well. And so you essentially have a system, that's like full of LLMs end-to-end, and that's extremely powerful. And then, this is more a bit more forward view, because I think this is something that is still more rare, but this is something we do a lot with our customers, is this idea of the flywheel, where essentially, based on all of this, we are going to use a lot of synthetic data generation, tune the models, deploy them, collect more data, and repeat that ad infinitum to optimize continuously against the metrics. And on this, the kind of metrics you can optimize against, by the way, include stuff that is like completely, like essentially purely, like truly the metric that you want. For instance, in a customer support system, you can literally optimize for escalation rate. Like, you literally have a reward in the reinforcement learning path that is escalation rate. So that really models that. We do work also with a consumer app, which I cannot disclose. We do optimization on user engagement. So we literally optimize for the likelihood of the user to reply, how engage and how like, how much will they engage with the chatbot and that sort of stuff. And this works. So it's really, really cool to have that shift, where now, instead of spending all of that time, if you think about it, here you were really in a paradigm where you have to define all of the behaviors of the model, like very explicitly, oh, now you do this, now you do that. Here, instead, you define the outcomes that you want. You create environments in which, the model can experiment with them. You run RL on that, you optimize end-to-end, and you obtain the behavior that you want, which is, I think, a much better way to approach this. Yeah, I think I'm a bit out of time. Typically, I like to talk about synthetic data. I will go quickly. I think something that's really exciting as well is another trend, but it's a bit adjacent to this, is the ability to use synthetic data to actually bridge the gap in terms of like being able to run RL. So stuff like AI judges, self-play, world models. I'll give you a fun one. So the idea of world model is, to replace, for instance, a real world, API that's really costly with an LLM. So have an LLM role play as an API. At the airline that I was mentioning, we ran into a problem where, once again, the lost luggage tracking system, During training, we tell them, okay, well, like, we need to access the system with XQPS, you know. They looked at us and they were like, oh, well, this is more than the production QPS. And I was like, well, you have a pre-prod environment, so we can scale it up. And they were like, there is no way that this is happening. No, like this, you know, like the production environment is already gigantic because this, you know, this is old code that runs very poorly. So we weren't able to run actually with the actual API during training because the load we will put on it will be larger than the production load. And believe me, the production load is actually quite large. So instead, what we do is that we have another LLM role play as the loss luggage tracking system. Literally role plays as it. Like we have a prompt for it. We have it's a very large quen. We have a prompt for it. We have some examples. We have a state tracking system. And literally role plays as a loss luggage tracking system. And that's a world model. This works really well, by the way. And this is kind of insane. I know some people do this for code, where instead of running the code, instead of actually executing the code, which is really costly and requires you to have all of these environments with like Docker images and all this, which is a nightmare to run all of these virtual machines, well, you can just ask an LLM for the output of the code. And actually it works. You would be surprised by how well this works on frontier models. And it's really like, really there is a perspective here, I think, of like LLMs doing this that is really cool. I'm more or less at time, so I'm not going to talk about case study, but you know, this is something we do in production with a lot of people tuning everything from like educational chatbot, text-to-SQL system, enterprise search, fraud detection, and really this pattern of building the tool use, you know, into the reasoning where the model discovers how to use the tool and all of this. This is an incredibly powerful pattern. This is something, I think this is one of the most exciting things actually about agents plus reinforcement learning. And I hope that I also got you excited about this idea. Happy to take any questions.